I just thought I'd kick off with just a quick question of my own, because this is what I was thinking, and this is, privilege of the job, really. When you were doing that calculation about chucking every bit of the mass of the observable universe, you sort of said, oh yeah, we're chucking in the protons, the neutrons, and then you also said, oh yeah, and the dark matter. Now the dark matter's that's the big thing, though, isn't it?
Yes.
That's presumably the thing that makes make it seem like we're in a black hole, because that's like 70%, 65%?
Well, dark matter itself, yeah, there's something like 5 or 6 times more dark matter in the universe than there is regular matter. Yes, that's true.
So does that not suggest that maybe that bit's wrong, which is why we're not in a black hole, and not the other bit of the calculation that's wrong?
That's a very good question. The answer is that no. Actually, the estimate of dark matter in the universe is very, very good. The problem with dark matter is the fact that we have no clue what it is. We know it exists. We know something that's doing this exists. That is completely incontrovertible. We look up to galaxies. Every galaxy that we see is spinning faster than it should if it's made of stuff that we can see with our eyes, right? If you take your favorite spiral galaxy from Hubble and you count up all the stuff you can see that's visible, and then you take your textbook on gravity, which I assume you all have on your bedside table, and you find how quickly a galaxy should be spinning based upon how much stuff there is there. You realize that it's spinning way faster than it should if it's only made up of visible stuff that we can see, stuff that interacts by electromagnetism. And if it's not light stuff, so that means that one of two things is wrong. Either gravity is wrong, and it's probably not. I mean, Einstein's general relativity is very, very well established. Or there's got to be more stuff there than what we can see with our eyes. And if it's not light, then it's dark. So that's where the dark part in dark matter means. It doesn't only mean mysterious. It also means that it doesn't interact by electromagnetism. And that calculation is pretty well solid. So that part is not going to change so much. The fact that we have no clue what it is, what kind of particle it is, that's the mysterious part. Every single one of you has about 1 billion particles of dark matter flowing through your body every second, unless it's not a particle, unless there's something else going on. So yeah, the short answer is that dark matter is very well established. However, we don't actually know if it's a particle. We suspect that at some point it will show up as a particle, but if it doesn't, then yeah, we would have to go back to the drawing board to see what's missing. And in fact, so that's the short answer. The longer answer is actually way more fascinating, and I hope you've had talks here by people that are really, for the last couple of decades, they've actually been digging into that other part. Maybe gravity is wrong. Maybe our understanding of general relativity has to be adjusted a bit. Again, for the longest time, this was sort of heresy. It's like, you can't touch Einstein at all. Oh my goodness. And in fact, the people that were working on modified gravity, several decades ago, were the crazy people. Like, they would just be, oh, that guy's working on modified gravity. Oh. But recently, there have been some fantastic, interesting ideas that are really kind of digging into this that, again, are complete, it's sort of like an Einstein thing. If we were to understand how to modify general relativity to account for what we see due to dark matter, it would also potentially require a total paradigm shift with respect to how we understand the fabric of space-time. Because, for example, my colleague Erik Verlinde in the Netherlands has this idea that, in fact, dark matter is not a particle, and in fact, gravity is not the force that we think it is. In fact, gravity is an emergent phenomenon due to the fact that the very fundamental fabric of space and time is, in fact, quantum qubits. So that part is even beyond me as a particle physicist. Every time he explains it, I'm just like, oh, wow. So
they do smoke a lot of strong stuff in there, I think, so I might explain it. So,
I didn't think about that. You're right.
Okay. Please stick your hand up enthusiastically so I can see you, and I'll get one of our stewards to come and see you. If you want to, there's 2 people there, one and then person behind.
Do you think that the properties of a black hole might change if there were, say, different concentrations of different types of matter that were making it up? Let's say it was all made up of dark matter.
Yeah, that's a good question, and the answer is probably not, because again, the only thing that makes a black hole, as far as we understand now, black holes are a consequence of gravity, right? That's basically a black hole is a point in space where gravity is completely won over every other force or pressure going on. So if you have something that causes gravitational, interaction, gravitational pull, then that can make a black hole, and it doesn't matter whether it's dark matter, because dark matter, we know, if the only thing we know about dark matter is, number one, it exists and that it interacts gravitationally. But we don't know if it interacts by anything else. And that's the big open question. If it only interacts gravitationally, again, that's the thing, the dark matter is the thing that's making these galaxies spin faster than they should. It's the thing that's sort of pushing it along due to gravity. But if dark matter only interacts gravitationally, then we're kind of, we're hosed. We don't really know how to, we don't know how to detect this thing. So we're hoping that either it interacts via one of the other forces in a very kind of weird indirect way, or maybe there's an extra force of nature that we haven't discovered yet, some kind of dark force. And that's things that we look for in collider experiments like the Large Hadron Collider. But it wouldn't matter at the end of the day what kind of stuff goes in there as long as it causes, gravitational interaction. And the sort of more details here, right, is it's not just matter, it's not just mass, it's not just matter that makes the black hole or that causes gravity, it's actually energy density as well. So and there's an energy mass equivalence. So the more detailed, again, once you have your textbook on gravity on your bedside table, you can see how this sort of like equivalence between energy and mass, it's energy and mass density that creates this thing that we perceive as gravity. So the particular way that it's made up wouldn't matter. So, for example, it's also a good question. That's one of the long-standing questions about black holes is that if they suck everything in, doesn't that ruin our understanding about like energy conservation and information, right? This is information paradox that I didn't have a chance to talk about at all. And we suspect that stuff that goes into a black hole, even though it is a one-way street for that, that's only a one-way street for a certain amount of time. So, for example, we suspect that black holes will evaporate, eventually radiate and give off all of the stuff that goes in, so it won't, violate energy conservation and these kind of things. But they will evaporate on a time scale that is like you can't even wrap your head around it, right? So, for example, I think it's a solar mass black hole. I forget, somebody fact check me on this, but I think it's something like a solar mass black hole will eventually completely evaporate and give up all of its stuff. But I think in something like 10 to the power 66 years, our current universe is only 10 to the power 10 years old. So you could do these calculations though, and they're just mind-boggling. So yeah, that's the long answer. The short answer is that because black holes are only a product of gravity, as far as we understand, then it doesn't matter what constitutes them. It'll still just all get sucked into this one thing.
And the question in front.
Yes, your hypothesis that we might live in the universe might be a great one big black hole,
yeah,
whether true or not, has some interesting consequence to it, and that is that you can have black holes within a black hole, and you might, within a regular black hole, have, if it was big enough and therefore the gravity wasn't strong enough within the event horizon, have lots of little black holes with their own event horizons and their own singularities.
Yes. Oh yes, no, you're completely right. I mean, if there's a question there, I'm happy to ask it, talk about it as well.
It is correct. You can have, yes.
Well, no, yeah, that's the thing. I think, because think about it, that's the consequence, right? This is mind-boggling, right? Like I said, the first time I came across the calculation, I was completely dumbfounded. It's like, again, I had to like literally do it myself, because you read it in a book, you're like, that can't be true. And then I do the calculation myself, and I'm like, maybe you got it wrong, and then I do it again, So, but it's definitely there, and that does mean that, again, this is sort of a technicality, right? If we live in an enormous black hole, again, like I said, currently I have no way to distinguish that from some other kind of hypothesis. But if we did, that does mean that inside of a black hole, you can have other black holes that come out. And that's sort of like that crazy diagram that I had, right? If our universe, in fact, was birthed from a black hole in some other universe, then it's sort of like this ongoing cycle. And that's also a nice answer to, a very speculative answer to this notion of like, where did the universe come from? It's like, what's before time equals zero, right? Well, okay, before time equals zero, we say that our universe is 13.8 billion years old. Before time equals zero, we came from another universe, and it's this constant cycle. So this, again, is completely untestable at the moment. So.
Hi, good evening. Just like to understand a bit about scale. So I think earlier in the talk you talked about black hole, if you like, distorting the universe, to form like a tunnel or a well. Yep.
Yeah.
How deep is that well? Is it like centimeters or meters or kilometers, light years?
So are you asking when you get closer to the center, how big is the thing, or like, how big is
not the diameter of the well, but how deep does it go?
Oh, that is a mind-blowing concept, because again, you have to think in ways that our brains are not trained to think, right? Now, again, that's like I said, I'm a physicist, and I can't wrap my head around what it physically means to have a point of infinite density and infinite curvature of space. And it gets very complex, where you have to think about, again, these wells that I show, that's a two-dimensional approximation of a three-dimensional, or multi-dimensional space, right? And so it's hard to even think about what that means. But the size sort of breaks down in a way, because once you get to such infinite curvature, the concept, so if there's any astrophysicists or like GR researchers in the audience, I totally understand that my description of space flowing is actually sort of depends on how you look at it. In fact, what's happening is the way that we measure things changes, this notion of a metric, right? And so you have to put a particular metric on space and time itself to be able to calculate anything about it, to be able to do anything with it. And you can put different metrics on it based upon different situations. And once you do that, once you get to a point of infinite curvature, the concept of length and distance completely breaks down. So I don't actually have a way to answer your question. Because all the other part is that, again, when you get closer to, when you have something like a singularity that pops out of your equations like this, it probably means, like I said, something that you're missing. There's like something that has to step in. That's, for example, why we'll eventually need to build a collider that gets to the Planck scale. This is not science fiction. Like, scientifically, we have to do that. We will have to do that to understand exactly what's happening at the Planck scale, because otherwise we'll never know. And we'll never know exactly what steps in, what new physics steps in to avoid these crazy singularities, right? There's probably something missing. And for those of you that know, people have been working on different ways to put gravity and quantum mechanics together for very many years. Things like superstring theory, these kinds of things, which we currently can't test. But if we had a large enough collider, we could start to test them. So yeah, it's not really an answerable question, because the concept of distance and length sort of starts to get twisted.
So we've got a question from right up in the gallery, and
Yes.
then also wave at me downstairs.
Hi.
For the
Thank
next
you,
question
very
as well.
interesting lecture.
Yes.
I just have a question. You explained to us that black holes are supposed to only suck energy and mass. But could you explain then this theory which suggests that there is also energy which escapes and leaves the black hole in the form of Hawking radiation?
Yes.
Thank you.
Right. So that's the open question. So if, for example, we had found miniature black holes at the Large Hadron Collider while Stephen Hawking was alive, Stephen Hawking would have received his Nobel Prize. Because this is something that he came up with, and some of his colleagues, that seemed crazy at the time. But again, people eventually realized, oh, that totally makes sense. That completely has to happen. So in a very, very rough sense, again, if there are actual astrophysicists in the audience, you can excoriate me later for my my shortcuts. But essentially what it means is that if you have, again, this event horizon, right? This event horizon, like I said, it imposes a boundary on physical space, right? You're either inside or you're out. And it gives a boundary with respect to what you can know about the universe. Beyond that, you can't know anything, or you can't go there. And the other direction is the same, right? So if you were then to zoom in on that, so it's like the gentleman's saying, it seems like it's a one-way street. I said this is a one-way street, right? For you as a human, if you go in, there's no way for you to get out, because there's no trajectory you could possibly take that leads back over the event horizon. It's just incontrovertible. You can't do that. However, if you were to zoom in on the event horizon itself and get smaller and smaller and smaller, like imagine you had some sort of magical thing, you could zoom in on this event horizon. Again, it's an event horizon that would be a sphere, the surface of a sphere. If you were to zoom in on that, smaller and smaller and smaller, down to the level that's closer to this Planck level, right? The Planck length, the length at which gravity and quantum mechanics have to have something to do with each other. Eventually you get to such a small enough level that the fluctuations and the uncertainties built into quantum mechanics itself start to come into play. So in fact, if you get small enough, we know that the fabric of space itself is actually a roiling fuzz of quantum mechanical stuff going on. And we know, just by calculations, if you were able to zoom in on the fabric of space small enough, you can actually have particle-antiparticle pairs that will pop out of the vacuum for just because they can. And you might think, well, that violates energy conservation. It doesn't, as long as these two particles they come into existence and then they annihilate quickly enough that the universe doesn't notice. In fact, you can do this. You can violate energy conservation as long as you do it within a small amount of time that the universe is not paying attention, right? And once this happens, like around you right now, if you were to able to zoom in on the very, very fabric of space, tiny, 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 you would see these antiparticle pairs popping into existence and immediately annihilating in a very, 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 very weak amount of radiation. Like you couldn't even calculate, you couldn't even measure it. But zoom in on the event horizon. At the event horizon, if you have a particle-antiparticle pair that pop into existence, one of them is on this side of the event horizon, inside the black hole. The other one's this way. This one inside immediately has no trajectory by which it can ever meet the other one. That means that this thing here will never find something to annihilate with. and it will end up radiating away from the black hole. As a result, again, that's sort of like it's a sort of a dumbed down version of actually what's going on, but that's a heuristic version of what's really going on. And as a result of that, we know that in fact black holes radiate. They will give off stuff, and this is what I was talking about this sort of like evaporation, right? We know that evaporating black holes eventually will evaporate. And if that's the case, you might be able to, so this is again sort of a conjecture, right? This notion that if stuff that's falling into a black hole, if it's only a one-way street, then then basically you can violate energy conservation, you can violate information, you have this information paradox. However, it turns out that other calculations show that you can avoid these catastrophic nonsensical things that the universe doesn't like if you just wait long enough. So for example, if you could, for a solar mass black hole or something, I hope I didn't get the number wrong, if you were able to wait for 10 to the 66 years, you would be able to, and you had a perfect device to basically catch all of the evaporation that's coming off of this black hole as it evaporates, you would be able to reconstruct what actually went into the black hole. Again, practically this is difficult. I don't know how you're going to be around with your measuring device for 10 to the power 66 years. But in principle, you can get around issues like this by doing that.
Fascinating. So we've
I
got
hope
a
that
question
answers your
here,
question.
question upstairs, question down here, then final question upstairs as well.
How exactly do physicists calculate the mass of the observable universe?
Oh, sorry, there you are. I'm sorry.
Yes.
Say again, I couldn't see you.
Sorry, how do physicists exactly calculate the mass of the observable universe?
Yeah, so you can do it from there's a few different ways you can do it. Basically what you can do is we know we basically can calculate what the size of the observable universe is, and then based upon other sorts of samplings of different parts of space that we know of, we can calculate on average how much stuff there is in the universe per, say, cubic meter or something like that. And this is basically an extrapolation based upon what we see around us. And there's no like everything in cosmology and astrophysics, it's based upon this notion that there's no reason to think that the properties, the laws of physics should be different here than far 93 billion light years away than they are here. So basically we do a density calculation of things around us, and then you can extrapolate that to everything that we can see. And once you do that, you end up with this enormous number.
So a question upstairs?
Yes.
Yeah, this idea that we're inside of a black hole is interesting. I guess you're saying as the observable universe expands, that operates like a event horizon. The other thing I would have thought is that in this context, the black hole is expanding. If there's mass outside of our observable universe, wouldn't that mass be getting pulled into our observable universe? So we could see an increase in the density of mass that would indicate that something was happening outside of our observable universe. Does that make sense?
Not exactly sure what you mean, but I mean, partially what you might be saying is that, so, we do know that our eventually, just because our observable universe, the size of that is set again by the fact that there is stuff that has never had a chance to send us a light signal that we have received, just based upon the speed of light, right? And we know that we combine those two things, the speed of light with the fact that the universe is expanding at a particular rate. And the farther things are away from us, the quicker things are expanding away from us, right? We know this is a fact. And then once you put those two things together, you can come up with this notion that, yes, eventually as this horizon, so to speak, this so-called cosmological event horizon, this has to grow just because we know that, eventually it will start encompassing things that we'll start to see things that we couldn't see before because finally we've waited long enough that a light signal could get to us, right? And so is that what you're talking about? Or?
Yeah, and if the black hole's outside of that, eating mass that's further out, would it become seen, and therefore we'd see more. The last question was about how do you measure the mass in the observable universe? Could it go up over time, which would indicate that maybe we were inside of a black hole?
Well, I think that is compensated by the fact that the density is not going to get higher because you're just going to get larger and you'll see more things, so the density should stay the same, right? So the volume grows, but then you see more things to take up that volume. So I'm not sure if I've answered your question. I'm happy to talk about it afterwards too, in detail.
We've got a question at the front here.
Yes.
Yes, thank you. In theory, could gravity be magnets? So positive atoms and negative atoms be attracted to each other?
So you mean?
Therefore causing gravity.
So you say magnetism?
Yes.
No, because we know that gravity has properties that magnetism by itself does not. So magnetism is not a force, right? We know that magnetism is just one half of this thing called electromagnetism, right? Which is a force in the current understanding of the way that three of the forces of nature work. Magnetism is a component of this, but it operates in slightly different ways, right? So magnetism, for those of you that know some physics, magnetism can't actually do work per se. It can actually bend things, but it can't make things happen in the same way that say electricity can. So electromagnetism is the fundamental force. So we wouldn't be able to say that gravity is a magnetic force, so to speak. But what we can do is we notice that partially what you might be saying is that we know that gravity is very similar to electromagnetism in one way because they're both so-called one-over-distance forces. The attraction of two things that are experiencing the force is the strength of that interaction is a product of how far away they are from each other. So that's very similar to what electromagnetism is. But in terms of gravity having some kind of like magnetism itself, we know that that's not the case.
Thank you.
Yeah.
I believe there's a final question upstairs.
Brilliant, yeah. Thank
Yes.
you very much for the lecture. I really enjoyed it.
Oh, thank you.
But yeah, I was just going to ask, you know how we've got like electromagnetic fields and like I guess a Higgs field, gravitational field. How does that differ to like we were saying with extra dimensions where gravity could act further? Is there a relation?
Yeah, partially. Yeah, okay. That's a very good question because if I understand correctly, it's sort of related to the following. So we know that for example, the question is, why is gravity so weak compared to these other forces? So one of the ways you could answer that is just say it's actually quite different. I mean, again, three of the known forces of nature, they arise due to rules of quantum field theory, right? And that's the rules of the very, very small. And this other force, gravity, is not actually a force like those. These other forces that we know of, the ones that we deal with the Large Hadron Collider, these are, if you look at them closely, they actually proceed by the individual particles exchanging other kinds of particles that are so-called force-carrying particles or vector gauge bosons, right? So for example, two particles, they get close to each other. It's kind of like you and your friend standing in an ice skating rink, right? You're just standing there with your ice skates on. And I have a heavy rock. I don't know why I brought a rock to the ice skating rink, but I did. And I throw you the rock. It's so heavy that as I throw it, I get pushed back. And as you catch it, you also get pushed back. So we have exchanged a force-carrying particle, and that's the way that the interaction proceeds. Gravity doesn't work that way, as far as we know. I mean, in principle it could, but we don't have any way to test that right now. Gravity, again, the force of gravity arises from a completely different mechanism, this general relativity based upon matter and energy density creating a sort of sinkhole in space itself. And so those two forces arise from completely different mechanisms. So as a result of that, if our understanding of gravity somehow evolved to the point where it's like, oh, we could see that this is actually on the same footing as these other forces, we might be able to say, well, maybe there's some kind of graviton, maybe there's some kind of thing that we're missing, that in principle we could put in and then understand this at a more fundamental level. And then what was the other part of your question? I'm sorry.
Yeah, it was just about like how that fits in with the extra dimension.
Oh, right. Yes. Okay. Thank you. Yes. And so, for example, to explain why gravity is so weak compared to these other ones, we postulate this notion that maybe gravity actually leaks into these other dimensions of space. So then you postulate that the fundamental structure of our universe is not 3 spatial dimensions and 1 of time, but maybe it's 4 spatial dimensions, maybe it's 10, maybe it's 26, right? But so then you have to then account for that in your calculations of everything, right? Not just gravity, but in principle, you also have to account for that in the other forces too. It turns out that if you do that for the other forces, they don't care about the dimensions. You can write down a version of that where gravity preferentially leaks into these other dimensions, and these other forces do not. So in a sense, it's okay. You don't have to, it won't change anything about these other forces. It won't change our understanding of the way these other forces and these other fields, which again are quantum fields. That's why the reason I bring up the concept of forces, right? Because the Higgs field, for example, it's this notion that, that's a very profound, it's a profound thing that we have to understand about nature, right? It's like, the thing about particle physics, right, when you first start to learn it, it's like, an electron is like a little chunk of something moving through space, through empty space. Turns out that's not the most fundamental way to think about particles. And in fact, the most fundamental way to think about an electron is not as a little chunk of something moving through space, or not even as a little wave moving through space. In fact, an electron is a tiny excitation in a field that exists everywhere all the time. So it'd be like, if you're playing with your cat on your bed, right, and you stretch the sheet tight, and you put your finger underneath the sheet and you move it around, and your cat chases this thing, right? So that finger is the electron. And so, in fact, the sheet, the field, is the fundamental object. And it turns out that those, for these other forces and the other particles that the particles that experience the forces that we know, they don't care so much about these extra dimensions. They don't have to. And so, I hope that answers your question.
Yeah, that's great. Thank you.
Yep.
I think we're just about out of time. We've got one question at the back there, and we can sneak in.
Please.
If you are measuring particle interactions on the level of the Planck length, wouldn't the position of the particle have to be defined beyond that the Heisenberg uncertainty principle will allow?
So yes, the Planck length is this level where we currently don't understand exactly what's going on below that, right? So currently the reason why we can't define distances or things like that are smaller than that, because eventually you get to the point where the uncertainties built into quantum mechanics make it impossible for you to do that. So for energy, that's not such a big deal. In fact, we can define energies that are much higher than the Planck energy. But for individual particles or individual things operating at that level, we can't. But for distances and times, yes, that's exactly what you're talking about. So if we were to somehow define quantum mechanics doesn't allow us to even define something physically meaningful that's smaller than the Planck scale, unless there's something we're missing, right? So and we're probably not, because quantum mechanics is very well established, and this is just sort of like intrinsic to our understanding of quantum mechanics. And the Heisenberg uncertainty principles those principles are also part and parcel intrinsic of our understanding of nature due to quantum mechanics. So there's probably no way around those, unless somebody comes up with a way to to put these together in a new way that we hadn't understood. But as it stands now, yeah, that's why I mentioned it's like there's no way for you to. Again, I can write down a number. I can write down on a piece of paper 10 to the power minus 54 meters. I can write that down, but it doesn't mean anything. There's no way for me to currently come up with a measuring device that could ever possibly measure something that's smaller than the Planck scale at the moment because of these quantum uncertainties.
Fantastic. I think that's just about it for this evening. Thank you all so much for coming. I think James will stick around for a little bit if you want to come and grab him and ask him all questions about gravitons and quantum gravity and his theory of everything. I'm sure
more details.
Pleased to answer those. But in the meantime, thank you all so much and see you soon. Take care. Good night.
Thank you.